Hi, Dr. Revis here with Watch Me Work It. In this video, I will show you how to choose the right thermodynamic formulas by systematic variable matching. This video will not solve the problems, but will show you how to set the problems up. In future videos, I'll show you how to actually find a solution. But for now, let's show you how to make sure you find the right equation. So here we go. Let's take a look at this one. Calculate the heat needed to raise 20.0 grams of water at 50 C to 90 degrees C. So here's how you do it. You simply mark off what you see. Calculate heat, that's Q. Needed to raise 27 grams, that's M. Of water, so since it's water, that's going to be a specific heat of water. In this video, I use S for specific heat. Some will use C. So S at T1 to T2, so that's a delta T. So I see my equation. For this, I'll use Q equals MS delta T. I'll put in the variables, I'll put in the values, and then I'll solve it through. And remember to watch your units. Units have to match here. If your answer is to be in kilojoules, then you'll need to do a conversion. Number two, how much energy is used for 33.3 grams of steam at 100 degrees C? It's heated to 150. Looks about the same, doesn't it? Q and mass, steam in this case. Aha, we'll use S, but in this case we have to use S for steam. S for water is 4.184 joule per gram degrees C. But for steam, it's 2.01 joule per gram degrees C. So we have an S, but we have to make sure it's steam. And this is 100 T1, T2. Therefore, I have a delta T. Works the same way. So this is Q equals MS. Make sure you note it's a steam. MS delta T. So that's how we'll solve those two. So these are formulas you use when there's a temperature change but no phase change. The next one, how many joules of heat are needed to melt 55 grams of ice at 0 C? In this particular case, how many joules? That's Q of heat are needed to melt. Melt, as soon as I see melt, melt is delta H fusion. And I have a mass here of ice at 0 degrees C. It's at this temperature. There is no temperature change. Okay, so the formula here is Q equals M mass times delta H of fusion. And that's what happens at 0. So this is a standard. I look on a standard table for delta H fusion of water. Okay, it's the same as ice. Next, how many kilojoules of heat are needed to condense 55 grams of water at 0 degrees C? In this particular case, we look for Q in kilojoules. In the first one, we look for joules. Here we look for kilojoules. Okay, of heat are needed to condense. Condense, that's going to actually should come out as a negative value. I'm just going to keep an eye on that. So are needed to condense 55 grams of water. So we have 55 grams. So that's going to be a mass of water. So there we go, water. So since that's going to be a condense, that's going to be a delta H vape. And at 100 degrees C, doesn't matter. My formula is Q equals M delta H vape. Now, you want to keep in mind this condensation, so you want to be aware of the signs. Also note, it asks for kilojoules. This value will come out in joules. So you're going to have to make one more conversion. Here it's going to be joules to kilojoules, because this is going to be 1 over 1,000. Because the standard for this delta H vape is in joules. So the formula, however, is Q equals M delta H vape. But watch your units. The next one, assuming that Coca-Cola has assuming that Coca-Cola has the same specific heat as water, calculate the amount of heat that it takes to transfer one can of Coke. Is cooled from 25 degrees C to 3 degrees C. So from this, that's T1, to this, okay, since it's cool, you're going to see that's going to be a negative value because of those. Here we have a mass for the can of Coke, all right? And so here, this looks like it's going to be a Q, where is it? Look for heat, Q here, and this is going to be a delta T. So we have Q equals ms delta T here, but we're going to need this answer in kilojoules, so I'm going to need to make a conversion here, 1 over 1,000 joules per kjoule. Okay, so that's how we set up. Again, mark off the variables you see in the problem, and that'll be your formula. Okay, the next one, 24.0 grams of butane has a molar mass of 58 gram per mole. This is not gram, this is gram per mole. That substance, 24 grams of that, is combust in a calorimeter submerged in 4.25 liters of water having this density. Calculate the heat, molar heat. Molar heat means I need Q over moles at the end. That's what I'm looking for. But what do I have? I have grams here, so let me put a mass here. A mass here, and don't really know what to do with this yet, but I just keep my eye on it. Submerged in water, this is liters. So I have 4.25 liters, but I don't work with liters, so I need to convert that to grams. So this liters has to be converted, liters to mils. So it's 1,000 for every one. And then I have to convert it by the density to mils to grams, because I need to work with mass in grams. This is 1 to 1. So this number is 4,250 grams. So now, let's back up and read it again. So we have grams of butane. It's combust in a calorimeter submerged in water. This formula looks like, and I have a temperature rise, so that's a delta T. So it looked like we would use Q equals ms delta T. However, I don't have an S for butane. I don't know that value. It's not published. Therefore, I have to use the water to find this, because I know that if I know the water, that's going to tell me how much energy is involved in this 24 grams. Okay, so in this case, you would have your, just plug these in for you. Your mass would be the 4,250 grams of water, because we know the specific heat of water is this value times this delta T. So we would get a value here, okay, and that's Q. So we get Q, and then after we get Q, we'll convert this 24 grams to moles. So that's 24 grams. I think you know how to do that. 24 grams times bar to grams per mole. And this is where I use the molar mass, 58.00 gram per every 1 mole. I get a value here. So these would be moles. And then I just put Q over moles, and that's my answer in kj, per mole. So that's how I find those. All right, let's go on, find the other. Again, the goal of this is to show you how to set these up. All right, the next one here is we have this solution of sugar. Okay, and so we have 25 grams of sugar, so that's a mass. And we have a molar mass. Don't know what to do it yet, but I suspect I'm going to convert these to moles at some point. At 27 degrees C, it's added to this. This is a T1. It's added to 115 grams of water, so that's a mass at 27. So this is the same T1. They start the same place. In a calorimeter, the temperature of the solution increases, so that's a T2. Therefore, I have a delta T in this problem. it's a specific heat capacity. There's my S, is this, and the heat capacity of the calorimeter is negligible, which means I can ignore the calorimeter value, calculate the molar heat. I look for Q. So there we have it. We'll use a Q equals MS here, delta T, and I'll get a Q value. All right, so this is Q. And then I'll do a similar process as before to find the moles of sugar. So I'll have 25.0 moles of sugar, grams of sugar. Convert that to moles of sugar, and use the molar mass, 180 to 1, and that will give me the moles. But here's the catch. This mass must include the total mass, because we have 25 grams of sugar and 115 grams. So your mass is going to be M1 plus M2. So your formula is really going to be Q equals M1 plus M2 S delta T, where your M is going to be 25.0 grams plus 115 grams S delta T. So that's how we would do that one, set it up. All right, let's take the next one here. So the next problem, we read it, and we have a reaction causes the temperature of the calorimeter to change from T1 to T2. Okay, so that's my calorimeter change. So there's a delta T that I have there. And the calorimeter has a heat capacity, that's the cap C, of 1,375 joule per degree C. How many kilojoules of heat are released? This answer is going to be, better be negative at the end. If it's not, I'm going to have to change my sign to negative. So here I see that, what do I have here? It didn't tell me anything about the mass. I don't see it there. So this tells me I have Q equals C, cap C, of the calorimeter times delta T. Okay? And keep in mind, however, the units here are in joule per degree C. So I'm going to have to do another conversion here to joules on the bottom, 1,000 to 1 kilojoule to get my answer Q in kilojoules. All right, so that's how we set it up. But again, we do this by paying attention to the units as we go through. All right, let's do another one. So here we have a calorimeter is filled with 2.5 liters of water. As soon as I see the liters of water, I know I don't work with liters. And since it's water, you know what? I know what that's going to be. That's going to be that many grams, because I know the density is 1. A reaction causes the temperature of the water, so I can get an S here. I have an M and an S to rise from 25 to 29.4. So I have a delta T. Okay, so I already have a Q, what I'm looking for here. Yep, I already have an MS delta T. The heat capacity of the water is shown here. That's specific heat, actually, is what that should be. So instead of heat capacity, that's specific heat capacity. Sometimes it's slang heat capacity, but it should be specific heat capacity. The heat capacity, the specific heat capacity is 4.184 joule per gram degree C. Yep, that's how I know it's specific heat. Mass tells me it's specific. The heat capacity of the calorimeter, that's big C cal, is that. So look like I have a couple of formulas going here. Look like I have a Q equals MS delta T, and look like I also have a Q equals big C cal here times delta T. So that's okay. You know what? I'll call this 2, I'll call this 1, and I'll say Q1 plus Q2 equals my final Q. And I'll put it in whatever units I need to. If I need kilojoules or joules, I'll make the conversion. So that's how you do it if you want to figure out which formulas to use for solving these types of problems. In the next video, I'll actually solve these.